welcome. Thank you all for joining us for this webinar for the Center for Advanced Transportation Mobility. This one is really kind of special to me because our speaker today is actually affiliated with each of our consortium members. So Dr. Raphael Patrick is a graduate of Embry-Riddle Aeronautical University, where he did both his undergrad and master's degree. Then he came to us at North Carolina A&T and pursued and completed his doctoral degree in industrial and systems engineering. And then he got hired at Virginia Tech, where he is right now conducting research. And of course, he's an assistant professor in the industrial and systems engineering department as well. So he has a team that he has been working with on one of our CATM projects. Actually, he has a couple of them, and they're kind of joined together. So I'm assuming that some of what he's going to present on links back to both projects. So I will turn the mic over to him and will allow him to introduce the rest of his team and continue with the presentation. Raphael?
Thank you, Miranda. Welcome, everyone. Thank you for joining us. Hope it's nice where you are, and welcome to our demo. So our presentation is going to be talking about auditory situational awareness for vehicle, pedestrian, communication systems, and this will be a Tesseract crosswalk module demonstration. No. There you go. One tap. There you go. All right. First, introducing our team. So we have 3 different teams really working with us. So I'll first introduce our research lab, which is the Human Impact Lab, and we'll talk a little about what the lab talks about. So Dr. Patrick, that's me. We have Esha, our PhD students. We have Miranda Brown, one of our master's students, and we have Nick. And they'll all give portions of their presentations about the work that they're doing for their graduate studies. On the other side, we have the Institute for Creative Arts and Technology. So we have Tanner Upthegrove that's here representing that. He's one of the PIs in the second project. And then Brandon Hale, which was here helping construct the equipment that we have. The other team is our Mind, Music, and Machine team. This is our first project, so I want to give them respects. That's Aberdeel Dam, which is a PhD candidate. And the PI for the first project, or the co-PI for the first project, is Phil or Dr. June. All right, so real quickly, our lab at Virginia Tech is called the Human Impact Lab. It stands for Immersive Multimodal Perception and Cognitions of Technologies. And essentially what we're looking at doing is studying the human effect on technology and technology's effect on humans. So we're really understanding these components of elaborating what happens when we engage with synergy between human components and technology components, and what it does as a whole. So we like to say we're dealing with psychology, engineering, and art. The art is really coming from our collaborations with ICAD. So we really get an opportunity to engage with our immersive technology in the 2 areas of our research is human technology interaction. So essentially dealing with, once you have the tech and the technology is rigid, how do we mold the human being or train the human being to be able to work with that technology? On the other side is the immersive multimodal perception and cognition, where we're really looking at the technology is very novel or new, and we're really taking the human being and molding them to the technology, really getting to understand what the limitations and capabilities of the human beings are. And we'll talk a little about some of the equipment that we use in our lab today throughout the presentation. All right, overall, we want to give respects to our sponsors. So like Miranda said, so we're sponsored through CATM. We have 2 specific projects. On this one, we're really looking at this concept of ensuring mobility for vulnerable populations. So we'll talk about the 2 projects that we've been working on for the last few years and how we've been engaged and moving closer to this goal of what CATM is looking at. All right, so ultimately, first, we're looking at our area of vulnerable populations is looking at pedestrian safety. Essentially, pedestrians is anyone crossing the street or engaging in any street-like activities. And recently, we have a law that was passed in Virginia that's really addressing this concept. We're poking right to what the concepts that we're engaging in our research. So drivers of any vehicle on highways shall stop when any pedestrian is crossing at any clearly marked crosswalk. Essentially, this means is at any marked crosswalk within the state of Virginia, and there's a person proceeding into that crosswalk, it is the duty of the driver to stop. On the opposite side, there's shared duty for the pedestrian. So no pedestrian shall enter or cross an intersection in disregard of approaching traffic. So the main project, the first one we're talking about, really deals with this form of distraction. So what happens when you're not paying attention to a crosswalk situation and you engage in a crosswalk? What is it like to engage with crosswalk situations? So we're really looking at this combination between driver, environment, perceptual acuity, and distractions, all leading to this concept of human performance or pedestrian safety performance. All right, ultimately, our project aims is to investigate the implementation of novel auditory-based human technology interfaces for vulnerable road populations. The road populations or users we're looking at are distracted and low visually impaired pedestrians during specific crosswalk incidences. Right, so how we're doing this is a mixture of research methods, human factors methods. We're looking at naturalistic observations, campus-wide surveys, subject matter expert interviews, and some empirical studies, and we'll talk about that today when it comes to labs and in control. So ultimately, the purpose of this is to better understand crosswalk and develop intervention techniques using the maximal components of auditory situation awareness. All right, ultimately, first phase, so the first project we're looking at that was run by Neal and the Tri-M Lab, we were working in collaboration with this, is our goals here are really to observe and document pedestrian and vehicle habits, really understand from a natural perspective of how people engage with crosswalks, especially at a campus. One thing we realized at a traditional road, pedestrians will yield to the vehicle because it's a very busy road. However, on college campuses, there's kind of this ownership of this is our road, right? We're here for college students. So there's this impasse between who should really yield for traffic. All right, so in this case, we really want to focus on in situations when it comes to crosswalks while on a college campus. Next step, once we have a better understanding of the actual environment itself, we want to move towards the development of a high fidelity virtual environment that represents, that is a representation of the actual environment so we can actually engage in safe street crossings. Once we've created that, we'll talk about a little bit about the creation of that development. And then we create this investigation to the impact of various street crossing situations, right? What happens when you're engaging in different headset devices? We have a couple of them there. So we're looking at over-the-ear bone conduction headsets. We'll talk a little bit about what BC is, and in-ear headsets. And the last component, which we actually shifted to our second project, is explore how vehicle to pedestrian alert systems can be created to increase pedestrian safety. And we'll talk about that as we get to the end of the webinar. All right, the first one is really looking at this concept of engaging in observations while on campus. So our first research team, you see in the video here, really just stood on campus. We went around and found the most busiest components of campus at the high peak time. So essentially, if anywhere you are in college campuses, it's during crossing behavior or in between classes. And we picked a location that was right after or before a roundabout. So there's really this tricky situation between what is the vehicle going to do and whether or not you're paying attention because of your situation. So ultimately, we really want to look at this concept of pedestrian behavior and also vehicle interactions. What happens when a pedestrian and a vehicle both meet at the crosswalk and need to engage? The next aspect of this is how can we communicate with these individuals, or looking at the communication devices that they already have on them. So on the left side, we'll briefly talk about this concept of bone conduction. So essentially, air conduction is using traditional means of hearing sound using your regular ears, in this case, the blue lines or the blue figure, while bone conduction is looking at vibrations of sound communicating directly through bone. So essentially means is you can keep your ears open while still being able to perceive the environment. So in this way, our research is really looking at whether or not your ears are being open or remain open or unoccluded, and how well you can perceive the environment. The picture in the middle is really the representation that we took. So we found the best location on campus, which seems to be a very heavy foot traffic location, two-part median, and is also a bus depot there. So it becomes very, very hard to visualize. If you look at the right, the sketch and the schematic on the bottom is really a breakdown of what that environment looks like. And we'll talk about the transitions from taking this natural environment into the virtual environment next. All right, so briefly, I'm going to pause because the first major step is actually capturing the audio files to then put into the file. So I'll go ahead and introduce Nick and let him come in and talk about that.
All right, thank you, Dr. Patrick. So the way we are capturing audio for this project is using a microphone like this, an ambisonics microphone. So ambisonics is a full sphere sound format, so it's pretty much a 3D representation of the soundscape that this microphone records. And to play it back, you need at least 4 speakers or 4 channels at a minimum to play back the audio. And when you record these files, they're recorded into a typical microphone format, which is A format. And then that A format is encoded into B format, which is ambisonics. And then that B format is then decoded into an arbitrary loudspeaker array, like the one you can see here, or a personalized headset or headphone display. So audio software is normally used like Reaper to transport this audio file into the Tesseract like this.
Thank you, Nick. Quick plug, even though it's not a part of this project, one thing I want to mention, Nick, as a master's student, is looking at taking some of the components of our research and expanding it to his study. If you notice, he was wearing some BC headsets. So one of the things that he is really looking at is how do we take these commercial devices that are available on Amazon and any third-party market, and how do we evaluate them to make sure they're actually presenting signals correctly? So one thing we want to point out here is if you look in the picture, the orange case in the top file are essentially our ambisonic microphones that Nick talked about. We're actually incorporating some of this into a class that I teach, and Tanner is essentially co-teaching with me at this point, where we actually take students learning the philosophies of understanding and the physiology of understanding sound, and we're actually giving them microphones to go out into the environment and actually capture these levels, and then being able to port the information back into the system. So we'll transition next about how we're actually taking the audio files that Nick talked about, actually collecting in the real world environment and bringing them into our virtual environment. All right. Tanner will go ahead, give an overview of this aspect.
Great, thank you. Virginia Tech is pretty special in that we have several, if not maybe the most spatial audio facilities in the country. That figure may not be true, but we have 10 high density loudspeaker arrays available for researchers to use. Next, please. Most of those are currently at the Moss Arts Center, and our flagship studio facility is called the Cube. It's a large black box theater with the internal dimensions being about 40 by 48 of usable space, which is perfect if you're doing multi-user studies, having ambulatory situations. We can turn this facility into a virtual environment visually and orally. We have several pieces of equipment to do that. We have large format projections, so we can project on the floors and the walls, projection screens, objects, and transform them into transform where you are into a virtual environment. 140 loudspeakers surrounding you in sort of a hemispherical pattern to create that spatialized audio that Nick mentioned earlier. We can decode ambisonics into this room natively. And if you recorded the bus driving by and you recorded the bus driving by in front of you, the sound will sound exactly the same in the cube with the bus driving by, all sorts of movements happening the same way. So this is a premier facility. We have lots of other technology to track users and objects in the space. Next, please. But Blacksburg is a little remote, and this is kind of a hard facility to get to and schedule. The cube itself, we often joke, is almost like a particle super collider in scheduling. It's almost booked a year out in advance, so it's hard to get research done in there. So to address that problem, as well as accessibility of having this technology for everybody, whether it's K-12 or bringing to conferences and presentations, or for artists, we designed the Tesseract. This was sponsored by the Commonwealth Cyber Initiative at first. Dr. Patrick and I received a grant to make the first Tesseract in 2020. And you're looking at a picture of one configuration of it early on. Next, please. So the idea here is it's like a mini cube. You have a lot of little loudspeakers that you can set up quickly on off-the-shelf stuff like theatrical truss, which you see in the picture, pipe, which you see on in the room with us right now, or pretty much any easy-to-assemble type of hardware that's portable and can go off-site. So this is our answer to bringing the cube to you to do research. There's other really interesting applications here. The picture you're looking at of the old Tesseract is inside the cube. So having multi-layered audio and the presentation of signals through different media concurrently is an active research topic, and that's what's kind of special about the space. So the room we're in now is called the Perform Studio. It's also like a mini cube. It's fixed as well. And much of the research that you're hearing about today happened in this room. And again, we can't bring this room out to the world, and we're kind of remote. So we have the Tesseract now where we can conduct the similar research in other spaces. Just to get an idea of a couple of the specs of the Tesseract, this is the current state of the art. So the picture shows the older version. We're currently inside of the new version that we've learned to make it better, faster, stronger, more accurate, etc. Everything is connected with Ethernet cables. So all the little loudspeakers around us get their power and signal from Ethernet. That means you don't have to run a separate power cable and an analog audio cable. and then figure out where they're going and have to run all your cable lengths ahead of time and cut them to length and get it right. So it gets rid of a lot of headache with setting up these systems as well by having a network-based approach. And that's what Power over Ethernet affords us. Next, please. So that's a lot about how we're presenting these signals and the studios and laboratories that we're doing them in. Next, I'd like to do a demonstration of how we take the recordings that Nick talked about, the spatial audio recordings, and then present them in a tesseract or a cube, or even another facility like or headphones, for example, even BC headphones. And now we're going to see a screen share of a software called Max. Max is a graphical programming language. It historically has been used by artists and engineers to do nonlinear audio work. So if you've used LabVIEW before, it's similar to LabVIEW. And if you're a musician and you've used an audio workstation, you can do much of the same work in there in an audio workstation in Max. It's full featured in terms of audio signal processing, audio workflows, as well as data workflows. So you can use it as a true coding environment. So we're looking at some code here. I wanted to show a couple things that tie together the capture with a microphone and then the reproduction in a loudspeaker array. So looking at this code, let's start from the end and work our way back. The tesseract we're in today has 16 loudspeakers, and this object takes the final audio and sends it to every individual loudspeaker. So every loudspeaker does get its own discrete signal. Above that, I have a volume slider. And further above that, I have an object called ambidecode. As Nick mentioned, ambisonics is first encoded into B format and then decoded. So this is kind of the last stop for the encoded ambisonic signal. To get an impression of how that works, let's take those field recordings that Nick captured and play them back so you can see how we put that together. The audio files captured are in wave format, so encoding B format ambisonics. You can encode it as B format, but the file container is a format we're used to, a wave or AIF. I'm going to take those recordings and drop them into a playlist so they show up in Max. Now I'm going to turn the sound card on now, and we can play them one at a time. So for everyone on Zoom, it's not really fair. We're sitting in this really beautiful 3D soundscape. We just heard some pedestrians walk by talking. We're hearing vehicles drive by. I mean, you might see us gesture even kind of looking left to right, even though there's nothing to see. We can hear the sound moving around inside of the tesseract. So playing back those sounds, it naturally bakes in the directionality of sound and then plays it back exactly how you heard it. We're in here just really enjoying this lush audio capture soundscape, but this is truly, you know, a testament to one reason why the tesseract is important, because Zoom clearly, this has been a problem for several years for a lot of us, having good audio quality. So having a tesseract available to listen to multi-channel audio and experience it and play it back correctly is really important. I'm sorry, I don't know what we can do to present it because it's not playing through a laptop. We're playing it through the room system, so we can't pipe it in. So that's something that we're going to have to improve upon. So maybe to talk a little more about the technical encoding and decoding while this is playing. On the left is the 4-channel audio that Nick described earlier. And we're taking that 4-channel audio and sending it to the decoder. The decoder then takes the audio and knows where the loudspeakers are in the room and can assign each loudspeaker its own audio feed. So this is next we'll look at a map. We measured the locations of all the loudspeakers. That's what all these numbers are. It's Cartesian coordinates of where the loudspeakers are. And this circle, this gray circle, is a top-down view of the tesseract. And I can feed it the loudspeaker coordinates and populate this decoder with the loudspeaker coordinates. As the ambisonic signal comes in, the decoder knows where each of these signals goes and acts like a virtual microphone to point out and tells each speaker where it's at in this 3D virtual space. Therefore, each speaker can play back accurately the sound field where kind of reverse what the microphone was doing. That's from a captured microphone. We can also encode signals, test signals into this format. Again, using kind of the same reverse method. So I'm going to turn off that playback. Now I'm going to play a test signal called a clicker. It works.
You hear that one?
Can't hear that one. So as I move around this number 1, I've color coded this sphere differently to show this is the encoder. We can encode point source single sound objects into this 3D sphere and combine them together with the captured scene. So we can have a virtual scene, a truly virtual scene, and a truly organic scene mixed together. So for some of these studies, that's what we're doing. We're taking recordings of, say, an ambulance it's a really good recording, but it's not in this ambisonics format, and virtually moving it through the sound sphere with the real recording of the crosswalk of the intersection that you see. So we can mix the worlds together and recreate with a high degree of fidelity the exact same experience. So if we match the same sound pressure level of the ambulance in real life to in here, we can recreate those signals in this room with repeatability and a high degree of fidelity every time. So this software, Max, we've been using it to receive commands from a virtual environment, and we can trigger automated moves. Like now I'm going to have that silly number 1 object just move around in a circle.
So Tanner, when you're moving that 1, that is a audio file or audio recording, and it's moving around the room that you're sitting in.
Exactly correct.
Okay.
And then we can have hundreds or even thousands of individual audio files moving at the same time or triggered based on a real auditory scene. Sorry, you had a...
No, I was saying, when we get to the CATM symposium, we'll make sure we bring the entire tesseract, so
Yeah.
you'll get a real feel of it.
How big is it?
The current tesseract that we're in has a 10-foot by 10-foot footprint, and it's about 8 feet tall. And it is modular, so it could get bigger. It could expand to be more loudspeakers. It could shrink down even to be a little smaller. But this seems like a good size. I don't know.
Let us know if we need to make it smaller for the symposium or bigger.
We'll cater to what you have.
Yeah.
Great.
Okay. Miranda, I'm gonna go back and share. So ultimately, the really good example of what Tanner talked about is the fact that we have all this great technology and it doesn't always translate to the audience, translate to the user. So now we're going to transition to the other aspect is now that we have this system and we're able to put sounds from the real world into the system, like we said, creating this digital twin, and we can make it as accurate as possible so we can increase the fidelity to whatever extent that we want. And then we have full range of messing with the signals, changing and altering the signals in any way. We're able to really engage with sound on a different level. So Randy, we're gonna move forward. So now we're gonna really talk about the next aspect of the project is moving into phase 2. Or phase 2 is really interested as what happens is we know what's going on with the crosswalk. We know how people are engaging. We know how people are walking. We know what the communication aspects are, nonverbal. What happens now when we're putting you into an environment and you have reduced capacity? In this case is you may be low vision, you may be distracted, or you may not have the ability to actually engage with the cars. So we're really looking at this aspect of subject matter expert engagement with vulnerable road users to establish this contextual requirements. So essentially we sent out in a survey that's in, I think it's going on right now, just to find out people that have these disabilities, how they're engaging in crosswalks. What is it like for them? And what are some of the technologies that they're currently using to help them engage with this? Once we know a little bit more about that, we'll bake that into the next aspect of our study. So number 2 is really looking at identifying and evaluating sensory input modalities to identify a valuable tool or viable tool for V2P systems, which are vehicle to person systems. So essentially, Miranda will talk a little bit about her project. What essentially saying is we talked about this concept between air and bone conduction, and we know that when you're using bone conduction, your ears remain open. So what happens if we use bone conduction while you're trying to cross the street and using that as a mode to communicate with you? But before we can do that, we had to understand from a theoretical standpoint, what is the transition, what is the communication speed between air conduction and bone conduction? So Miranda will talk a little bit about her project when we get to that point. Next is, now that we've created this environment, we'll talk a little about we've talked about the auditory version of it, but we'll talk about the virtual visual creation of the environment and how we pipe them both together. So once this environment was created, we then put people into the environment, alter the signals, and have them actually do this virtual version of a Frogger situation, right? What is it like to actually cross the street? There's full visuals, full auditory, and the only protection here is you don't get hit by the car, right? So you're able to actually engage in street crossings that we can manipulate the situations like scientists really do. And the last one is ultimately create a portable version of this. So we're not just testing with the isolated group in Blacksburg, Virginia, but we can take this around the country, especially to HBCUs that have different populations, and we can take this to different campuses that have different cultures when it comes to crosswalk activity. Next. All right, so my last slide, and then we'll let the students pipe in. So essentially, we call this one-to-one audio plus visual immersive environment or immersive test bed. It's essentially saying the test rat with the visual components. So here is our first group of participants or researchers that was looking at a version of this. So on the left side, you'll see the participant in real time crossing a real crosswalk, meaning the blue cases, the blue lines outlined as a crosswalk. And in the visual case, you'll see it's a direct replica between what this participant is seeing and what they're seeing in the virtual world. So essentially, that's why we call it a one-to-one comparison, right? So you're able to actually walk across the crosswalk while you're walking in the virtual environment. All right. Major things about this, the benefits to this is it's done in Unreal Engine, which means it's a game engine, and we have a lot of manipulation and modality when it comes to that. And the last aspect of this is it's safe, repeatable, and reliable. We can run a participant through the same exact scenario multiple times, and the only issue we have is fatigue. Right. So all the other components of this, we have full control. Once we have a better understanding of this, we can take it out to the real world and like the test road, the actual VTTI test road, and assess this in a real version of this later on. One more. All right, so I'll pause right now. Miranda will briefly talk about her research, is looking at the components of the theoretical side of the technologies and the devices.
Okay, so as Dr. Patrick said, I've been looking at the most effective way to communicate with the pedestrians. So I'm comparing air conduction and bone conduction headphones. I'm also looking at various bone conduction locations and various frequencies at these locations. So this is trying to determine the capabilities and limitations of these V2P communication systems using the pedestrian's personal listening devices. What I have here is a little bit of like a live sample of some of my data that I've been collecting. We present the tone to the participant, which are the big blue boxes at the top, and the little button pushes that you can see at the bottom, that's where the pedestrian or the participant is reacting to the sound that's being played. And I'm going to look at the reaction time. As I said, for air conduction versus bone conduction, we have 4 different bone conduction locations, which we're testing: condyle, mastoid, the forehead, and the inion. And we're testing them at various frequencies. So we're doing 250, 500, 1K, 2K, 4K, 6K, and 8K. And we're trying to figure out what is the most efficient way to present alert to them to signal whether or not it is safe to cross.
Hey, Miranda. So one of the interesting aspects of this is one of the pieces of equipment that we acquired for this is a BioPack system. And a BioPack system is basically like a module system for physiological measurements. It allows us to tack on sensors. In this case, we're only using a reaction time sensor, so it's a reaction button situation. But the good thing about this, it provides us with the software that we can sync up the timing of the actual signals through the audiometer or any other test signal like that. And we can sync it up to the user response. So if you look, like Miranda mentioned, the blue bars here are really the signal itself, and then the box frames in the bottom are really giving this indication of when the user is responding to this. Ultimately, when we first started doing this, we want to look at this chain of presenting a signal once it hits your brain, and then when you respond to it, which is a classical human factors or informational processing model. However, through deeper research, we found out the ERP, which is the event action response, that portion of it was really difficult to get to just because you had to have very quiet situations, right? So it was really hard for us to really get the brain stimulation without having really, really quiet and isolated environments. So what we ultimately did is bypass the brain activity and move directly to the response. So we're still in the same component of the chain, and we've connected with some BC researchers to really understand how we can study this in more depth. So hopefully one of them will come back for their PhD and study that next. All right, Ren. All right, next one, so I'll give a short introduction. Esha is our PhD student, and she's working on the next component of that. So once we have the details from Miranda's study, understanding the latencies between the air conduction and bone conduction, Esha will then take that data and port it back into the software and then give us that latency to equalize both situations between our air conduction and bone conduction. And I'll stop there and let Esha explain her study.
Hello, everyone. This is Esha Mahendran, and I'm the PhD student working on this project. My study uses the test bed that Dr. Patrick just mentioned that is safe, reliable, and repeatable. For that reason, using that, I want to test out the optimal navigational aid system that could help vulnerable road users cross unsignalized crosswalks. And I'll be testing the optimal type of device, the best signaling method, and the best way of presenting those signaling methods across 2 visual modes, as seen in these 2 pictures on the slide. The first mode is the visual mode, where you can see all of the visual cues in the environment, including the day of the time of day, the road, and the car. Whereas in the non-visual mode, your visibility is reduced. As a participant, you would not be able to see most of the environment, just the crosswalk and the car when it's approaching. Since this experiment is conducted through virtual reality, we can ensure that the safety of our participants while testing, because this cannot be tested in real life. And I want to evaluate participant performance in using these pedestrian alerting systems. Next slide, please. So what I expect to achieve from this study is to find what could be the most effective navigational system in poorly lit environment, just like the figure in the previous slide, and what kind of signaling method or what kind of information and signals would be the most effective to facilitate safe crossing behavior on crosswalks. And at the end of each trial, I would ask my participants about their preferences on each system, which would help us determine which navigational aid system was the best or was the most convenient to use. And next slide, please.
All right, thank you, Esha. All right, so now we're going to go into the next part of our demo. So Esha talked about this concept of creating this virtual environment and manipulating these different situations to see whether or not we can increase the safety of our vulnerable pedestrians. So this demo is really going to give us an opportunity to see what the virtual environment is going to be like. One thing that you noticed in the bottom right-hand corner was this aspect of training. So we believe education is really it, educating people of how to cross the street, when to cross the street, and when not to. The laws changing is really good, so we have some protection, but ultimately we realize it's a training situation. You really have to understand the danger you could be in by engaging in vulnerable street crossings. So what we want to do in this demo is give you an opportunity to really see what the environment looks like. It should be a live demo, so we'll be able to kind of take a look around, and then we'll flip back between the modes just so you get a chance to see what the environment looks like. When you're ready, you can go ahead and share. Share your screen. So ultimately how we do this is we have a bunch of Oculus headsets. The lab itself is also studying on the HCI side, studying what it's like to have immersive headsets.
Could I have screen sharing, please?
Oh, Dr. McBride, can you add screen sharing for Esha? So ultimately what we're looking at is the HTI side of our lab is really interested in what happens when you have virtual reality and you're using VR as a mode of technology enhancement. Got it?
Give me just a second. I just had to locate her.
You're good to go. So one of the things is we'll talk about this. This is an Oculus Quest number 2. They have transitioned to Oculus 3s, but our Oculus 2s are still viable. We're still able to use these. Our lab itself has about like 60 or so of these headsets. So like Tanner mentioned, in the cube, we can do large scale testing of this. So one of the things we're looking at for future projects, possibly ESHA study number 2, is what is it like when you're going through group crossings? One of the feedbacks or results that we found out with study number 1 was individual street crossing can be dangerous, especially if you're distracted. However, street crossing in groups was really the critical factor, right? When you're crossing the street, especially at a college campus, and you're in kind of like this cohort, whether or not it's your friends or just a group of people you're walking with, that really influences the way that you cross. So what we want to look at later on, once we get the original version of this going and Esha gets her first study going, we're going to go look at the multiple comparisons. What happens when you're walking in a group? Do you follow the herd? Do you sit back and wait? All right, so good to go. All right, so normally what it is, participant comes in, we give them a headset. The headset, if you notice, is untethered, which allows the participant to walk around the entire test facility. And once you get into the headset, you should be able to see what I'm seeing.
Can you see the taskbar?
Yep.
All right.
All right, so in this situation, what we usually do is give a few minutes for a participant to kind of get acclimated because VR is pretty novel to most people. So you don't really have an opportunity to try it at your house. But when we come to this campus, we really like to let them sit in the environment. As you notice, it's kind of void of any distractors. Originally, if you remember the first video, we had it replicating the Squires, which is our cafeteria here. But then we realized there's a lot of distractions. So what we did is we dumbed it down just to make sure you can see the cars. As you see one kind of crossing by us here.
Esha, can you you're showing the developer mode? Okay, thank you.
Okay.
Perfect, here we go. Now we're seeing what Dr. Patrick is seeing.
All right. I like to call this Morpheus's waiting room.
All right, so here you can see the car coming by.
We're waiting on mine. I'm still loading on mine. But if you can see it on your screen, you're good.
Yes. All right. And when that happens, we would send a signal on to ensure
Yeah, I'm still in the Morpheus waiting room though. But as long as it's on the screen, you're good. It says loading here, so it might be porting over.
So this is the visual mode. And now I'll play a demonstration of the non-visual mode. And
Dark mode. And that's the way. So one of the things we want to do, especially my audio. One of the major conditions we want to look at was, like we said, vulnerable populations. So this understanding of what happens when you have reduced vision. Our biggest issue was recruiting populations like that. So ultimately, we found out that if we can take a normal population of students and the participants we were able to get, we can just degrade their vision. Obviously, we know this is not a direct comparison. It's not going to translate over. But we're really looking at trust in some ways, this component of these signals. So like you said, Miranda was looking at the signaling latency and timing. Where we're looking at the signal, if you can hear now, the dissonant signal. This is a signal created by the Auditory Systems Lab by Dr. Casali and Dr. Lee, looking at a really, really annoying signal that can get your attention. So what we ultimately want to do was put you in the headset here, black out your visuals so you can't rely on your eyes and kind of play the Frogger game, and only rely on the auditory senses you get. So in this case, we really want to look at this component of taking your information that you can hear and responding to the information. So this is why we believe having the tesseract is really important, is because sometimes you don't need the visuals, right? If we can get the tesseract and play all of the signals through the tesseract from a purely auditory component, we can still see whether or not you can do active crossings. So one of the things we look at here is we can take the visual component, dumb them down just through the tesseract, or we can bring the full installation and do the visual plus the auditory component together. All right. Go. All right. Everything else in here? Did the black screen come up?
Yeah.
Okay. All right. Click over. Okay. Asha. All right. Ultimately, thank you for your time. We want to give you just an overview of what we're working on here at Tech, us with ICAT. So thank you very much for ICAT and giving us the opportunity to use the Perform Studio throughout the year. Thank you very much, students, for being diligent students and getting work done. Shout out, like we said, to the past teams and anybody else, our sponsors. Thank you very much to DOT and CATM for all the work you've done and supporting us in our research. And hopefully, over the next 3 years, we'll say, Ash graduating really soon, we'll be able to advance this research and keep moving forward. And like Tanner mentioned before, we also have another project in the CCI area, so the cybersecurity domain. So we're really interested to see how we can take this information and this type of project and move it over to the security aspect too. So we can look at vulnerable transportation, vulnerable populations when it comes to transportation, immersive multimodal media when it comes to just understanding how sound is, and ultimately in the defense area of how we can take this and provide information to users. So thank you very much for your time, and we'll pause now for any questions. Thank you.
Yes, thank you, Dr. Patrick and team. I appreciate the work that you all are doing and putting into this. I know it's not always easy to make these simulated devices to be able to directly mimic the real world. So I know that takes a lot of work, and I appreciate the efforts that you all are putting into making this happen for these particular projects. Do you want to open up the floor and see if there are any questions?
Yeah, sure.
From our audience? And please just feel free to unmute yourself. I see Mr. Kelly Taft. I saw his hand was up for a second.
Good afternoon. Good afternoon, everyone. I just had a quick question concerning commercial vehicles. Did you notice any difference between the private automobiles versus commercial vehicles, the larger vehicles?
Yeah, so originally in the first study, since we're staying on the college campus, we don't get too many of the commercial vehicles. We'll get a few of them going through doing shipments and deliveries. But in our case, we would consider our commercial vehicles, let me know if I'm wrong, as our buses, right? On our campus, the major vehicle that we have a really good bus system here at Virginia Tech, and our students, some of them don't even need cars because our buses will run every 15 minutes on the second. They do not miss. So we have this constant cycle of buses going through our campus. The other aspect of that I think you're kind of alluding to is like the loudness of these vehicles, right? So we do have traditional combustion engine vehicles, like most places do, but we actually have a lot of electrical vehicles that come to our campus as well. And we've definitely noticed that there's a difference between the intensity levels. So your ability to be aware of these vehicles because of the electric component. To exacerbate that, we actually have some buses that are electric buses, right? Which means you have these large scale commercial vehicles that you can't even hear. So that's why we think in our campus is really important they've gotten to the point where they've even put signs on the floor that says, hey, look up, right? Just because we know that certain students are just like in their zone when they're moving and going from classes, right? We kind of, get baked after just like doing so much work, they kind of lose sight of what's going on. So we're really trying to figure out how we can get them involved and understand these things better. The other thing is our campus is going through evolution, meaning they're growing, and we're actually moving all of our buses to one isolated area on campus. So which means it's going to become this hot spot of this cross activity. So yes, we did see a difference between the type of vehicles, and we definitely saw how people respond to the different vehicles. Essentially, people are not going to run in front of a bus, but they're okay to cross in front of a car. So we need to make sure that situation is the same, right? You feel the same fear when it comes to a bus, a car, or electric vehicle.
Thank you.
Thank you.
Any additional questions?
I have a question.
Okay.
Have you done some studies in which vehicle is actually looking at the pedestrian position and then giving out alert signal? For example, if the pedestrian is in the middle of the crosswalk, and if you give a very high-pitched sound, like try to communicate a vehicle with the pedestrian, and otherwise vehicle would have easily crossed, but given that sound, he will go into a shock, basically, and will went into a situation which is called deer in headlights. Basically, it's gonna stop and actually a collision can occur. So are you guys looking at the statement when situation only when the pedestrian is trying to cross the street, or you're looking at relative pedestrian position on the crosswalk with respect to your research?
Yeah, currently right now, study number 1. So the first project looked at position before you initiated your cross. So before you started your cross, vehicles were moving. We had some latent signals in the background, like an ambulance signal that I talked about, so you can understand directionality when it comes to other signals. And then Esha's study is moving over, similar to what you mentioned about, we've created this thing called hitboxes. Essentially is when the vehicle comes into this special area at a designated distance away from the crosswalk and then initiates a signal to the pedestrian, or it's the opposite version, is it will turn off when they're in the hitbox. So right now we're talking about before they proceed in the crossing, but Esha is still building her study number 2 and number 3. So if that's not something you were working on, I'm pretty sure Esha just took some notes. But we're really interested in this concept is what happens throughout the entire time of crossing. But no, to answer specifically, we're not looking at the deer in the headlights as of right now. We're looking at before, so the initiating of the decision to cross based on the information you're receiving.
Can I add one thing? As an adjacent research topic that this team is not working on, but part of this team overlaps with, is addressing a similar problem. I'd like the approach and idea that the vehicle is responsible, because one human-centered factor with this challenge, say in Europe, electric vehicles were not detectable by some people at a crosswalk. So a suggestion was for people that have a vision impairment or an audio impairment, wear a device that gives them a notification when they cross. However, there was a large social problem with that, because there could be a potential stigma with wearing a device, especially in Europe, when, historically people that were identified by some kind of worn thing was a problem. So I think the approach of making the vehicle responsible for transmitting the information, as opposed to an individual that has to have something, is an interesting area to explore even further, especially the kind of the social and personal considerations involved.
Thank you for that, Tanner. Hopefully that was the purpose of our original survey, right? The initial survey is to get an understanding of technology acceptance, right? What they would accept and what they would not accept, because of, like Tanner mentioned, the stigma of, I don't want to be identified as the person that's the problem in this situation. We're all responsible for it. So hopefully we get some of those results back from our survey that we're distributing quite widely. So we're able to get some at the university level. We're able to get some locally. So Greensboro, so the Industries of the Blind, some groups like that. And then we're able to distribute them nationally as well. So if you have any groups like that you think could give us some background or some information like that, we'll definitely share the survey with you. But thank you for that, Tanner. Any comments, Esha, since this is your study, anything on that?
I'd like to add 2 comments. One is that in the literature, there are several studies where the cars have a display right next to their plate number that shows symbols or just plain words saying do not cross, car approaching, or it shows a sad face when the car is really close to the pedestrian. That is one thing. And second thing about having a device that is not really seen on people. In my study, we are exploring a tactile device option, which is a Wooger, which you can attach to your chest. So it's not really, it's very inconspicuous. Not everybody on the street could see it, and it could send vibrations to the person wearing it, and they can be aware that a car is approaching them.
Thank you for that. Yeah, that's the main reason we're looking at pedestrian, so personal listing devices. We were trying to tap, as Esha was alluding to, we were trying to tap into this concept of if you're already wearing it, can we just pipe into it and give you information, salient information through the devices you're already wearing? So we're really trying to look at those devices that people can currently be wearing or potentially would be wearing. Thank you, Esha. Yeah.
Thank you so much for all the insight. I really enjoyed the presentation, and I learned a lot. Actually, I am working on pedestrian vehicle interactions, and I'm finishing my PhD as well. And I'm mainly working on vehicle control, but it was very, very insightful. Thank you.
All right, well, congratulations and good luck. Get to the finish line.
And I'm curious, just in the literature that you've been reviewing, is there a lot of documentation about the number of pedestrian vehicle accidents with the implementation of so many electric vehicles?
Do you mean to say that after the implementation of this communication system, there have been accidents or not?
Well, not the communication systems, but just in general, since they've been implementing more and more electric vehicles, have you been seeing more, has the literature been documenting more accidents than before in these types of crosswalk situations?
Yes, definitely. It is an upcoming problem, or even a present problem, really. And I think in this country, I'm not in an East Asian country, I'm not sure if it was Singapore or South Korea, they pushed for a motion to add signals to the car, to add signals to electric vehicles, which is kind of defeating the whole purpose of silent electrical vehicles. It's basically designing something and then saying, oh, we forgot this feature. So that is one legal intervention that has taken place, as of my knowledge.
We have one of the original co-PIs on this project. Tanner was involved with this one as well. Dr. Mike Rowan, he's now at Penn State. Yeah. He did a lot of research when it comes to electrical vehicles. He actually did a study with blind participants at the crosswalk, or not actually crossing, they were sitting in a chair while a car was coming towards them. He was looking at how close does a car need to be for you to be able to detect it auditorily? So he really looked at that concept, and he found out that an electrical vehicle needs to be way too close for you to detect it, and you cannot respond to that in time. So in the United States, he was one of the ones that were part of, I think it was GM. Yep. He was involved with GM, and they actually implemented this requirement that, like Esha said, every electrical vehicle actually is too low. Right, the volume should be at a threshold. So they actually implemented this requirement for all electrical vehicles to make this artificial noise to alert for participants. So the fact, like Esha alluded, is the design of this concept of this car was to be a quiet car, less energy, more efficient. However, the unintended consequence was it was silent. And since it was a silent vehicle, it created these accidents. But yeah, there's, I think, recently sent over some papers that were talking about this increase in traffic fatality instances, incursions, deaths, just because of the fact that people cannot sense the vehicle. But hopefully having this test bed gives us a chance to kind of push those thresholds and see how good we can get for that.
Okay, thank you. And real quick, I saw Venkatesh Pandey. Dr. Pandey, did you still have a question?
Thanks for the insightful talk. That was really like enlightening in terms of like this topic is new to me. So I was just curious about have you considered like the impact of extreme weather events in the pedestrian vehicle interactions, and because I'm coming it from like a resiliency point of view, like how will these technologies be impacted when we have like hurricanes, flooding, or I'm sure visibility gets lowered, but I'm curious to hear your thoughts.
Yeah, we haven't looked at weather, just because like our VR person that built our environment graduated and we can't keep them here too long. But developing the actual visual environment has been a little bit difficult, but luckily because of this grant, we were able to hire him as a consultant. So one of the good things is we were able to further advance the technology that we made the first time, even though our student graduated. So I actually took over that aspect and we're gonna keep growing it. Ultimately, it's where the students wanna take it, but definitely we think environmental is one of the major things. As human factors people, we have a Venn diagram that we always talk about: the human, the technology, and then the environment. So we definitely think we're really talking about the human when it comes to Miranda's study. We have a lot about the technology when it comes to Nick, Esha, and Tanner's aspect, but the environment isn't really big into what we're looking at now. We just stuck to the classical campus environment, but the components of that is the visual component, right? Reducing the visual aspect of what you can see. But we definitely think the environment plays a role into it. One last piece, I'll let anybody else chime in, is that's why we also move towards personal listening devices. We were really hoping that we can pipe into a device that you're already wearing, right? We know that human beings, especially young teenagers, young adults, love listening to music. And it does not matter what environment they're in, they're going to listen to their music. So if we know that those devices, especially personal listening devices, can overcome all of these external factors, why not just, give them a slight pause in their music, tell them something is going on, and let them resume their music, right? So it's more of a factor of us being able to pipe into something that's already existed and on the users, instead of trying to add something additional to it. But environmental factors is definitely something that could be interesting. Esha, comments?
I already mentioned limited visibility. When you mentioned your point, I was thinking of reduced hearing, sorry. So in that case, again, I'd like to point back to having vibration devices, like haptic devices that give you those notifications. Those could be helpful in an event like a hurricane.
Yeah.
And I think early in one of the earlier studies, we did have condition for adding auditory masking, spatial auditory masking, so you could simulate rain or some other event that would obfuscate, say, an electric vehicle's perfectly minimum threshold loudspeaker that's playing the right signal, but you can't hear in a rainstorm. So there are conditions that we don't have many, but I think that's a great point to have conditions about weather, and we can do auditory masking very easily, as shown in the synthetic environment.
Great. Well, thank you again. We appreciate the presentation. It was very enlightening. I like bringing presentations that are not your typical transportation presentation. So showing the interaction between transportation and all these other disciplines, I think is really important, especially when it comes to our workforce development efforts, letting people see that their interest areas do have a place in the transportation domain as well. So I appreciate the work that you all are doing and how you are transitioning some of your work to benefit the transportation workforce and the users of transportation as well. So thank you again. And I do look forward to seeing this simulation put in action, the Tesseract system put in action during our symposium. So for those who are not aware, we are planning a symposium for CATM, and we're actually having a joint symposium with our new regional center, the Center for Regional and Rural Connected Communities, in April. So you'll be seeing more information about that as well. So again, thank you all for attending.